find out.
Oh, yeah.
All right, so chapter 6. So the main topic here is the inverse and implicit function terms. So you've seen the latter last semester, and it went by in a flurry, and you guys were all upset because you didn't understand it 100%. And I said, don't worry, we're going to do it again. So we're doing it again. And we'll also be discussing manifolds more deeply as we head into chapter 8. All right, so the key proposition that goes into the key ingredient that goes into this is understanding things that are called contraction mappings. And so as a warm-up exercise for this, I want to do an example that's in the book. Some of you have done this on your calculators, I'm sure. Suppose you pick a number at random. Let's say, just to be nice, let's say, pick an x0 in the interval from 0 to 1. Put it in your calculator. Make sure you're in radian mode. So with your calculator in radian mode, repeatedly hit the cosine button. What happens? Have any of you ever tried doing this?
Yeah.
Or the sine button, or the tangent button.
It goes to solve cosine x equals x. It goes to x.
So what? Okay, that's correct, Cameron. What is it? So what's going on? So here's the graph of the cosine function from 0 to pi over 2. Now what happens if you pick an x and you punch the cosine button?
You go up to that height.
So you go up to this height. And I'm going to say x sub k plus 1 is the cosine of x sub k. So I'm defining a sequence this way of real numbers. I start with x0, I hit the cosine key, that gives me x1. I plug x1 in, I hit the cosine key, that gives me x2. How do you see that in the picture? So here's x1.
Put x1 back on the x-axis and then go up again.
Alright, so the way I'm going to put x1 back on the x-axis is to cheat and draw the line y equals x.
Then you know exactly where the point is.
So to put x1 on the x-axis, I'm going to go over here to where I intersect the line y equals x, and then I'm going to come down here, and that'll be x1. And then I hit the cosine key again, so I'm now at x sub 2. Agreed? Well, now I want to get x sub 2 back on the x-axis. So I do the same thing. I follow this point over to the line y equals x. And now that's x2 down here. Now I do cosine of x2. Well, that puts me up here. That's x3 now. I go over, back down, that's x3. So if you've never seen this, it's a really cool picture. You draw a cobweb. Start at x0, and then you trace around and do x0 goes up, over, down, up, down, over, up, down. No, it's very different. So what I'm doing is spiraling my way in, closer and closer to, as Cameron said earlier, the point where the two curves cross, where y equals x crosses the cosine graph.
Last semester we had a web work problem that was this, I think. It was like
It's related
x,
to this.
k
It's
plus
talking-
5
yeah.
over x and x over 4.
So last semester you did have a web work problem to find a fixed point, assuming it exists. So what I'm doing here is saying you have f of x. You have f of x equal to cosine x, and by looking at this sequence, just as you did in that homework problem, we're claiming, or we're guessing anyway, that the sequence goes to A, where f of A equals A, and that's graphically what's going on here, right? As you spiral it. Now, the issue is, well, what is it about the cosine function that makes this spiral in rather than doing some random jumping around and not converging?
It's always decreasing.
It always takes values between 0 and 1.
It's bounded.
So there is something more going on than what you guys are saying, but those are all ingredients, I think. So what is it about f that guarantees we converge to a fixed point? So you guys proved in homework last semester that if it converges, it has to converge to a fixed point, because f is continuous. So you proved in homework, I'll get to you in a second, Dennis. You proved in homework that f continuous implies if the sequence converges, it converges to a fixed point. All right, Dennis.
Is it due to the function being convex?
Yeah, that's what I was gonna say, if it's spat out.
There's more going on.
For sine, would it be just 0?
Yeah, it's going to go to 0.
'Cause I'm doing my calculus.
It takes much longer.
For sine? Mm-mm.
Like, more iterations, I think, because if near 0, it just keeps getting the same, near the same.
Actually, you're right. You're actually right. So we'll understand all of these things in a few minutes when I get a little further. Right. So Cameron mentioned Newton's method. I'm going to come back to that whenever the next class is. Newton's method is a similar iterative scheme to this, but you're not repeating the function. So do you guys remember what Newton's method is about? But what are you doing with Newton's method? You're looking for?
Solutions to the tangent line.
No.
Solutions to the equation.
You want a root. So you're seeking a root of a function g, let's say at least c1, and we might want better. Near a starting point. So the picture for Newton's method is so I'll just draw not a very complicated graph here. Picture for Newton's method is you're looking, this is the graph of G here, and you're looking for a place it crosses, and suppose you started at x0. So we're not doing what we did here. You're instead doing what? So you so Newton's idea was to go up and draw the tangent line and see where the tangent line crosses the x-axis and iterate that process. And as you can see, that's getting me, well, my picture's slightly off here. I did not draw the right tangent line. but even if I'd drawn the correct one, it would have been very close. And so you can see you're getting there very, very quickly. And in this case, what are you doing? Well, when you solve for x sub k plus 1, you're finding the x-coordinate of the line through xk g of xk, whoops, xk g of xk, that's the point. You draw the tangent line, and then this is x sub k plus 1. So I'll let you write down the point-slope formula and solve, and what you get is it's exactly xk minus g of xk over g prime of xk. So if you solve for the y, for the x-intercept of that line, you'll get this. So the slope is g prime at xk, and if you solve for where that line crosses, y equals 0, you get exactly this x-coordinate. Notice that if you were at a root to start with, you would stay there. If g were already 0, then xk plus 1 would be xk. You also notice there's a problem with the derivative
It's 0.
is near 0.
Makes sense.
Which makes sense because if the curve is very flat, the tangent line shoots very far away. That's not good, right? And if g prime is 0, the tangent line is parallel to the x-axis, so there is no next point. Okay, so this formula makes sense, and now this tells you that you're doing an iteration of where this is the f. So now we're iterating f of x, which is x minus g of x over g prime of x. We're plugging in initial value x1 into that and defining the sequence recursively. So what we're going to talk about today and whenever the next class is how you use this general scheme to actually be guaranteed solutions.
Newton's method, does it need to be like monotone on that integral or something in order to ever approach the root?
So normally, and I'll do a little bit of discussing of this next class, you don't want the derivative anywhere near 0. And so what you're going to see when I get through what I'm about to discuss is you're going to have to actually take a derivative of this thing and understand it. And so you're going to need some bounds on the derivative of g and on the second derivative.
Is there a multivariable version of Newton's method?
Yes. That will be in one of your homework problems next week.
Great.
So, here's a definition. And yes, Jonathan, this is a definition to put on your definition list. Let x be a subset of Rn. A function f, and I'm going to put a vector sign on f to remind you that we're mapping vectors to vectors. So notice I'm supposed to have a function that takes things in x and returns answers that are also in x. I'm not saying anything yet. So a function that sends points of x to points of x is called a contraction mapping. If, and it's very important to get your quantifiers in the right order here, there is some constant c that's possibly 0, although that's not very interesting, but strictly less than 1, so that the function contracts distance by a factor of at least c. So that for every pair of points in the domain, the distance between f of them is at most this constant times the original distance.
So there's a single number C.
There's a single number C that works universally for everybody. Now, one of your homework problems that's due, presumably Wednesday, is asking you to pay attention to how important it is that this C be less than 1. So it's not good enough to say that this number is less than this number. So the warning here, the danger sign, is we are not saying the statement f of x minus f of y is less than x minus y distance. Do you see the difference?
Well,
If I continue.
if the top one's true, then the bottom one's true, but if the bottom one's true, then the top one isn't, always.
Right. Everyone catch that? Which one's a stronger requirement on f?
The C.
The top one. This is requiring more of f than this one is.
Why? Because C is less than. You just figure I take C covers for every.
Yeah.
Just to say this means that for each pair x and y, there is some c that works, but the c might not be fixed
Okay.
as x and y move around.
Although theoretically, if C is at its max value, it is equivalent to the bottom.
No, because the max value, the soup of the c's could be 1.
Well, I thought C has to be less than 1.
But the soup of numbers that are less than 1 could still be 1.
And then it would include 1 where the bottom one doesn't. Because
No,
it's like less
this
than-
would still, if you're saying for each x and y, so that's why I said order of quantifiers is very important here. If you're saying for each x and y there is a c with this property, then this is still true. But you might not be able to get a c that works for everybody simultaneously. So the hint is one of your homework problems is exactly exploring this.
So they're right, we're gonna write one closer.
Yeah.
Sorry?
Look at me. I think she was asking something.
So is that because, this is for the homework problem too, is that because when it goes to infinity, it goes to 1 and so cannot satisfy C?
That's what you need to see, right?
There's always a value that are just slightly
So
bigger.
be very careful about the statement here. Okay, so what is true if you have a contraction mapping? So the theorem we're going to prove, it's called the contraction mapping principle, and this is actually used in infinite dimensional calculus applications all over economics and differential equations theory and physical applications as well. So this is actually a baby version of something that's extremely powerful. Let X in Rn be a closed subset. If F mapping X to X is a contraction mapping, then F has a unique fixed point. So what I'm trying to suggest with the Newton's method reference is that finding fixed points of things is actually a very useful and interesting thing to do. And you can solve lots of mathematics, economics, physics, whatever problems by setting them up as fixed point problems that you're trying to solve. And then there's theory that, such as this, that helps you solve them. Why do I need closed?
If it's open, could it like be approaching something on the border where it's like not included? It's kind of like the sequences that approach something that isn't
Yeah.
in the set.
So can you give me a totally stupid example? Dennis?
The cosine function missing the point where it intersects with y equals x.
Okay. Even stupider.
Just one.
So Dennis wants me to use some interval, but then take a point out of the middle of it somewhere. I'm going to
The
do
line.
something simpler.
The line just, I guess, one, flat line one with zero miss, no.
You don't need flat line 1.
Y equals x,
Y equals
with
x.
zero missing.
With 0 missing. So how about you take x to be an interval where 0 is missing, and f of x equals x.
It's not a contraction method, though, is it?
Oh, gee, that's not a contraction mapping, is it?
Let's do one half.
What's the distance if you apply f? The distance is the same as the original. What do you want to do if you want to make it shrink?
Point
Add a
.9.
c,
Not add,
or multiply by c.
where c is.
plus
One
one.
half.
So for example, half x. So now if you do the graphical thing we were doing earlier, you're taking the line, you're on this domain, and you're taking the exact same picture we were drawing there with y equals x, that was in green, and you're doing the same thing where you start somewhere, you start at some x naught, you take f of it, you go over, and you go, that's your new x1, right? Now you do f of x1, that puts you here, so you go down, and then you go over, and you go down, and you go over. So instead of the spider web, it looks like a
Cross
Staircase.
staircase going to,
0.
which ain't there, because we destroyed closedness by removing 0. Okay? This line.
Would it work if we removed a point that wasn't the point it was approaching?
Yes. But you wouldn't be guaranteed
Yeah.
by the theorem, but that's right. Okay, so closed, you can tell it's going to come like a lot of proofs we did last semester. We're going to define some sequence when we do the proof that has a convergent subsequence, and we're going to want to know that convergent subsequence converges to something in X. And in fact, since I didn't put compactness anywhere, there won't be anything in subsequences. It will just be sequences. So what's an application? Well, so I'm gonna restate something I stated among all the other things on Friday, but didn't stop to prove it. So I'm actually going to prove it today. So remember I talked about the mean value inequality? So we stated that on Friday. We had some hypothesis that we had a reasonably shaped set and F that was C1 on it. And we said if you took any 2 points and the set were convex, meaning that you could draw the line segment joining in A and B, then we got that the distance between f of A and f of B was at most, remember this thing? Max
Max of the norm.
of the norm of the derivative at all points between A and B. So I wrote this as a closed interval notation, which you guys didn't like, but this is just my shorthand for saying line segment from A to B.
So basically, if we
Times, sorry, A minus B. Magnitude. Yep.
so we make the norm of the matrix always less than 1 for contraction mapping.
Be careful. Okay. So Cameron's saying, if you know what about these numbers,
They're all less than 1.
then why? How can I pick a C? You're right. But
Oh, because we did that homework problem where there's like the opposite of the norm. There's like the smallest amount.
no.
You can
Oh,
stretch.
no. It's easier than that. Why isn't this the same thing we were discussing over here, where the c's might get closer and closer to 1? You're taking a maximum over a closed interval. Right? So because f is c1, the norm of the derivative is a continuous function. So the closed interval from a to b is a compact set. So the max value theorem says there is a maximum, and since all the numbers are less than 1, that maximum will be less than 1. So as Cameron suggests, set c equal to the max of all these if the norm of df at x is always less than 1 for all x in the interval. So that's going to be a major application that we're going to use over and over and over again in this chapter. We're going to apply this theorem to a function that comes from this setting, where we have some condition on the derivative so that we know this is true. Any questions?
What exactly do you mean by f has a unique fixed point?
It means there is a fixed point. There's a point x and x, so that f of x equals x, and there's only one. In fact, that's your first homework problem that's due Wednesday, is to prove if you have a contraction mapping, you can have at most one fixed point. That should be a one-line proof, guys.
Don't we prove it's continuous? Because I've looked at the homework.
That's part of the homework, but that's not relevant for what I just said.
It's part of the, yeah, it's very.
Okay, so I want to actually give a proof of this before I just start discussing the contraction mapping proof. So proof of the mean value inequality. So I hinted at you guys the other day that it was an application, actually the other day I wrote it backwards, did I not? I put B here and A here.
It doesn't matter.
It doesn't matter, but it looks more what you're used to if I do it. It looks more like what you're used to with the mean value theorem if I put it in the usual order. Doesn't matter, of course, as Daniel says. Consider the function. So I felt like on Friday you guys really got into the fact that we were using so many different fees, so I figured we should use another fee.
Yeah.
Maybe we should
We got fee squiggle, fee straight.
So I'm going to define a function phi from the interval 0, 1 to r by phi of t is the function f of so I better have Rm here because f back to Rm. Phi of t is f of a plus t times b minus a. So what am I doing with capital Phi? I'm parametrizing the line segment that goes from A to B, am I not? When t is 0,
And you're at A.
I'm at A, and this is the direction vector for the line, and when t is 1, I'm at the point B. And then I'm applying f. Now, what does the chain rule say the derivative of phi is?
Derivative f.
Derivative of f evaluated at that.
Times t.
So you take the derivative of f at the inner function times the derivative of
The inner function.
the inner function, which is
C minus
B minus A.
b minus a.
T is
Terms
variable.
of T.
T is the variable. I don't differentiate with respect to T. So I'm taking df at whatever point, multiplying by the direction vector b minus a, and that of course gives me a vector in Rm, which, if you like, means I'm taking component by component. I'm taking the directional derivative of each component function of f in the direction of that vector. All right, fundamental theorem of calculus, lest you forget. What happens if I integrate a derivative of somebody from 0 to 1?
The NP derivative evaluated from
You get the somebody.
It's just phi of.
Phi of
F1 minus
phi of 1 minus phi of 0. And that's still true for vector functions because I'm just doing it component by component. So remember, when I do the integral of a vector, like integrating velocity, you get change in position, and you can think of that by integrating component by component of the function. Is that okay? So phi of 1 minus phi of 0 happens to be whom? Who? Happens to be this, without the bars. F of b minus f of a. So if I want to estimate how big this is, I want to estimate how big that integral is.
other components.
Hmm? All right, well, this is easy. So, the magnitude of f of b minus f of a is the magnitude of this integral and I'm just going to keep on putting in what I know. The derivative of capital phi is what's at the top of the board there. So I do df at point on the line times direction vector of the line segment, and I integrate that dt.
Don't we know what phi of 1 is and phi of 0 is?
What do you mean no? It's,
Well,
it's
we
that.
We already know what it is though, we have values.
But I'm trying to prove something that says how big that change is, and presumably that's going to come from looking at this. Okay.
What do we have? Oh wait, no, never mind.
Now you have to recall stuff from last semester. I know that's asking a lot, especially when you might not have school tomorrow. You have a matrix A and a vector x. What's the biggest it can be?
Norm of
Norm of A
times x.
times the norm of x, times the length of x. So recall, this came out immediately from linearity once we defined the norm. So we did it in class last semester, it's in the book. You used it in homework. Yes, Gabe?
Semi-unrelated question. If we show that the norm of matrix is 0, does that mean the matrix is, I guess, 0?
So what am I going to do? I'm going to say, well, the biggest this can be is the integral. So we actually used this last semester when I talked about arc length. Go back and look in chapter 3. We did do this. The magnitude of the integral of somebody is less than or equal to the integral of the magnitude of the vector. This is like the triangle inequality, but we actually proved this in class last semester. Well, what did we just say about the magnitude of this vector? The biggest it can be is the norm of the derivative matrix times the length of the vector b minus a, and then I integrate dt. Well, the b minus a is constant. And what do I know about this? Well, it's less than or equal to that. That's just saying take the max of all of those things over the whole interval. So as t varies from 0 to 1, all of these numbers are less than or equal to the max of them all. Well, then that says, I can say it's less than or equal to what I get if I put the max here, multiplied by the length of b minus a, and integrate that constant from 0 to 1. What's the integral of a constant from 0 to 1? That's the constant. Right? Because as t varies from 0 to 1, the point x is varying on the line segment from a to b. So that's taking the max of this is giving me that. Gabe, you wanted to say something? Oh. So there it is once and for all. So we're going to use that a lot.
Wait, so we just proved the important application?
Yes. So, right. So from the mean value inequality, Cameron suggested what the application I had in mind was, which is if you know all these are less than 1, then you have a contraction mapping.
Okay.
So if on your set X, whatever it is, the max of all of these, not just in the interval, but everywhere is less than 1, then you know F is a contraction mapping. All right, so how's the proof going to go?
Wait, the proof of the contraction mapping principle?
Yeah.
Okay.
I always start by defining the sequence.
So we're probably going to use a sequence.
Maybe some numbers.
So the idea of the proof is pick any x to start, pick any x naught, and do exactly what we were doing at the beginning of class. Iterate the function. Define a sequence recursively. So the computer science people should like that word. By saying, once you have xk, plug it into f, and that gives you your next element, x sub k plus 1. You proved last semester, again, that if this sequence converges, the thing it converges to is a fixed point. So we know goal, show the sequence converges. And then continuity, oh wait, I didn't assume continuity. I just assumed it was a contraction mapping.
We proved in homework the contraction mappings.
Right, so contraction maps are continuous. So since contraction mappings are continuous, said limit must be a fixed point, and why must said limit be in capital X? Why does it make sense to say it's a fixed point? It has to be in the domain. X is closed. So this, and the limit must be in X because it's a limit of a sequence that's in X, and X is closed. Now, some of you have taken Math 3100 or Math 2410, but a lot of you haven't. So those of you who are fancy, so that's how many people are fancy? 1, 2.
Gabe, you're not that.
Well,
So yeah, so a lot of you haven't had 3100 yet. So the fancy students learned a word that also was in a challenge problem last semester.
crochet.
Coochie
Not
swap.
man. Oh, yeah, that's cool.
It's mentioned in the book.
Yeah, we had
Did I actually assign it?
Yeah.
Oh, then everybody's fancy.
Oh yeah.
So what you can
More
show
fine dining.
is that because f is a contraction mapping, this sequence is going to be Cauchy, and then because x is closed, that means it has to converge. For the rest of us, I'm going to not use that. Now everybody should aspire to be fancy and actually learn how to use the Cauchy stuff, but I'm going to give you a more plebeian proof that's based on something from Calc 2. So the Cauchy sequence proof actually, for you fancy people, works in infinite dimensions as well. So if you were working all in an infinite dimensional vector space, and you've seen a few of those, that is actually a good approach. What I'm about to do for the plebeian approach only works in Rn. Well, plebes have to pay for it somewhere. So, do you guys recall something from Calc 2 or 3100, that there's a notion for a sequence of real numbers to converge absolutely?
Yeah.
So there's a notion of convergence of a series, and there's a notion of absolute convergence.
Yeah, but that's
Oh, yeah.
absolutely
No,
valid.
okay.
So,
like that from both
if an are all real numbers now, I'm not doing vectors. If you have real numbers, we say the series is absolutely convergent if the series of absolute values converges. Is every series absolutely convergent?
No.
No. Do you know?
Well, any series that's not convergent is also not absolutely convergent.
Yeah.
No.
Negative one
Any
yes.
series that is absolutely convergent applies to convection.
Okay, that's where I'm headed. But can you have a convergent series that's not absolutely
Yes.
convergent?
Yeah.
The famous example is
Negative 1 being ground.
alternating harmonic series. However, so Ken just said what I want. I want a proposition from basic calculus here that if the absolute value converges, if the series of absolute values converges, that's called absolutely convergent, then the series itself must be convergent. Now, if you actually took 3100 and used Adam's notes for it, he actually gives a proof in that course using Cauchy sequences. But I'm going to give you guys an easier proof. And then we'll finish the proof, haha, tomorrow. All right, so here's the sneaky proof. And no, Jonathan, you're not responsible for this on the test. All I do expect you to remember is comparison for series. So if you have one series that's dominated by another series and the dominating series converges, then the original one does. So recall, if you have a series of non-negative terms and they're bounded above by C-ends and the C-end series converges, then the series B-ends converges. This is called the comparison test. If you don't remember why this is true and have no idea about it, go look it up, and if you still don't understand, come talk to me about it. So here's the sneaky trick. Out of this AN, I'm going to build a new series. I'm going to take AN plus its absolute value. This
So the
log.
sneaky proof is, what if CN converges to something that's like greater than 0?
No, I'm doing the summation.
Oh, okay, sorry.
So remember that if a series is going to converge, the the terms themselves, the actual
Okay.
terms must go to 0.
Okay, makes sense.
But what we're saying is the bn's get squeezed to 0 quickly enough by the cn's, which are going to 0. So here's the sneak. Consider an plus absolute value of an. What can you tell me if I take a real number and add it to its absolute value?
It is negative 0.
Greater than or equal to 0.
So if an is negative, this is 0. And if an is positive, so what's the most it can be? So, all right, it's at least 0 always. Agreed? Oh, I'm sorry. So I'm going to assume an's are. No, okay. So if an is negative, then you guys have told me I get a 0 here. If an is positive, I get something certainly that's bigger. And if an is 0, it's certainly at least 0. So bn is at least 0. And what's the most it can be?
2an.
Twice magnitude A.
Twice the absolute value of an.
Yeah.
This works when an is positive. And it also works when an is negative. It happens that bn is 0, but it's for sure less than twice the absolute value of an. You see where I'm headed with this? If you know the absolute value series converges, what do you know about this series? And ergo,
Bn.
a series of bn's converge. Finish the proof.
Don't erase the definition.
Why?
That's what we're proving.
I'm not getting there today.
Sorry, just trying to help.
Then you said, wait, you want us to finish the?
We're not done yet. So the bn series converges. So what? What are we trying to prove?
That's what I'm not sure.
Trying to prove the series of an converges. Knowing that the absolute value series converges. So you have the absolute value series converges and the bn series converges. How do you get an back? Is that right? This series converges, this series converges, and the sum of convergent series
Is it
is again a convergent series.
How do you set it? Oh,
Right? If you look at the formula for bn, you just solve for an. So anytime you have the sum or difference of two convergent series, that series converges. It's a basic exercise that they probably had to prove on their 3100 test that they just took. So we're done. The series of an converges. So what we're going to do on tomorrow, is apply this with vectors now and actually prove that if I take my sequence, I'm going to concoct from my sequence a new sequence to which I'm going to be able to apply this proposition to each of its coordinates. And that's how we'll prove that the x is convergent.